Hey Wheat North, Mr. Igler here. Another thing that we need to talk about regarding weak acids is the percent dissociation, which, as the name suggests, is just the percentage of it that is ionizing into its ions. I'm just going to go through some examples here because I think that's going to be the best way to go over this stuff. There's not really any notes to take per se because you've done percentages before. It's always a part over a whole. Every percentage is like that. So we just need to figure out what the part is that it's asking about and what the whole is, what the original amount is. So let's look at this example. Ascorbic acid is also known as vitamin C, and it's diprotic, so it has two protons, but we're only going to be looking at the first one coming off, so don't worry about that just yet. We have a Ka, and it asks what is the percent of the molecules that ionize in a 1.5 molar solution. Now the 1.5 molar solution is important because that's the original, that's the whole amount of the HA. So let's go ahead and write an equilibrium reaction, and we have one proton coming off. And I'm just going to skip the initial and the change rows of the ice table and just go right to the equilibrium. We know that it's going to be plus x and plus x, so our K equation is going to be x squared over 1.5 minus x. Now we can neglect x in this case because we have 1.5 as our starting concentration, and the Ka is much smaller than that, several orders of magnitude smaller. So I'm going to cancel out the x and the subtraction, and you end up with x being 1.1 times 10 to the negative second. Now let's pause a minute and think about what that is. The x is your H plus concentration. So if we want to do percent dissociation, we want to take the quantity of H plus divided by the whole of the total amount, which is the 1.5, right? So just put your H plus over your HA. And that comes out to 0.73%. So with a small Ka like this, less than 1% of the molecules are dissociating. Now what about in a 0.1 molar solution? You might think that this should not matter, right? The Ka is constant, and so the percentage dissociated should be constant as well. Well, let's go ahead and actually calculate it out. We have the same Ka. It's going to be the same equilibrium expression, this time 0.1 instead of 1.5, because my initial concentration is 0.1. Again, I can neglect x. It's a little bit of a closer call here, but I'm still about 1,000 times smaller than my initial concentration, so that's fine. And my x ends up being 2.8 times 10 to the negative third. Now, when you put this as part over whole of your, remembering that your whole is now 0.1, it actually comes out to 2.8%, which is surprising that it dissociates more in a more dilute solution. That's actually an important point to maybe mark down in your notes. A weak acid dissociates more if it's more diluted. The reason is, the best way to explain it, I think, for our purposes, is just understanding that Q is going to be smaller when you dilute it. When you dilute every species in solution, Q is going to drop because we have two products and one reactant. And if Q is going down, then it's going to form more products to get back to equilibrium. Now, what about calculating the Ka? Let's say we're given a percent dissociation. Carbonic acid is dissolved in your blood and it's drawn out through exhaling CO2. This helps you maintain homeostasis in your circulatory system, in your whole body's pH levels. It's 0.59% dissociated in a solution that's 0.0125 molar. So let's calculate the Ka. Now let's kind of pause for a second and think about what we need. The Ka expression would look like this. We're solving for the Ka, and so we're going to need all three concentrations of these, but all we have is this percent dissociated. So let's start with what we're given here. We know that we have a percentage dissociated. Let's go ahead and turn that into a decimal, and then it's going to be part over whole. The part is still the amount of hydrogen ion concentration over the total carbonic acid concentration. Now we know what this one is. It's 0.0125, right? That was given. And so now we just need to solve for H plus. Now, think about it for a second. We still need the HCO3 minus ion concentration. This is the bicarbonate ion. What would that concentration be? It would actually be the exact same as the H plus, because in that dissociation, every H plus that you create, you're also creating HCO3 minus. And so they're going to be in a 1-to-1 ratio, and so they're actually going to be identical. And that's pretty convenient for calculating the Ka because you actually just square it, put that over your original concentration, that is your HA concentration. Now technically there would be a minus x in here, but it's going to be so small we're going to keep this at 0.0125. And then your Ka comes out to 1.5 times 10 to the negative 7th. And that's it. With percent dissociation, you just need to be able to calculate the percentage that dissociated and calculate the Ka from that percentage, going either way. All right, this is Mr. Yergler signing out.